probably gonna be complicated. They don't like each other yet.
Look, I'm out of date.
Continue with this. I want to recap where we are, or how we even started all this stuff, and then continue. Okay. So we started with the following. You have two charges. The question is, how much force do they exert on one another? So here goes Coulomb's law. And it's the force that, let's say, charge 1 exerts on charge 2 is equal to 1 over 4 pi epsilon naught, the product of the two charges divided by the distance between the two charges, right? The separation between the two charges. And this is the force between them. But if you want specifically the force that charge 1 exerts on charge 2, we can put a vector on that. And that this is the position vector pointing from 1 to 2. And you have to put r hat. So that's the force exerted, that charge 1 exerts on charge 2. And then we said, okay, what if we just have one charge? What does it produce? And we said an electric field. The problem became, find me the electric field, and then I can tell you what the force is. The force on a charge sitting in an electric field is simply the product of that charge times the electric field in which it sits in, right? Just like we said, gravitation, always when you're confused about electric fields, go back to gravitation. A mass sits in a gravitational field G, the force is just the product of the mass and the gravitational field G, M times G. Here we have charges and fields, Q times E. So electric fields. So if you just have a charge Q here, and you're at a distance r away from it, it will produce an electric field away from itself if it's positive. If it's negatively charged, then the electric field will be towards the charge. And the electric field for a point charge is Q over 4 pi epsilon naught r hat divided by r squared. That's the electric field for a point charge. And so far so good, right? Okay. Then we said, okay, what if I don't have a point charge and I don't have 2 of them or 3? I have a continuous charge distribution, infinitely many. What do I do? Right? If we have lots of them. So if you have a continuous charge distribution, we have 3 configurations. The charge distribution can be linear along the line. In that case, you have lambda, so linear. You will have lambda. It's charge over length. And so, if I have, here's a linear charge distribution. This is a linear charge distribution. And let's say I cut a little segment here of length dx. And the question is, how much charge would I expect to find in that little length dx? And the answer is dq is just lambda times dx, right? So dq would be how much you would expect to find in that little length dx. And so far, we're good? Okay. The next is the area. Charge could be spread over an area. So maybe, let's do this. Area. In that case, you have sigma, which is charge over area. Charge over area. So if you have, let's say, some shape like this rectangle, and you ask, how much charge do I expect to find in a little area dA, which is dx in this direction, dy in this direction. How much charge do I expect to find in here, dq? Then dq would just be sigma times the area, this little area, which is dA. If it's rectangular coordinates, it's just dA is just dx times dy. That's how much charge you expect to find. And finally, the volume charge distribution. Oh, sometimes I would write eta, right, in my lecture notes or my worksheets, and that's because just some other books, they use eta. Some other books use eta. And when we did thermodynamics, eta used to be the thermal efficiency, but if you see it in the context of electricity, eta is not thermal efficiency. There is no, we're not talking about thermodynamics. But I would try to write sigma everywhere, but just in case. So volume charge distribution. This one tends to be uniform between all the books. It has the simple rho, and it is charge over volume. Charge over volume. And so dq would be rho minus dc, which is the volume. In this case, so maybe your shape, a shape that looks like this, and it's just some material, and the charge is spread over a volume. So if you take a little cube like this, which is dx this way, dy this way, and dc this way, so the volume is going to be dx times dy times dc. In practice, we usually reduce, we're never going to do a double integral or a triple integral. We always reduce it. There is enough symmetry to reduce it to just one integral. Okay? You will see when we do Gauss's law how this works. All right. So some charge distributions that we did was some results that we had. Some results. I'll just write the two main ones. The one that we should always know, the infinite line. So let's say this is lambda, infinite line of charge. Infinite line. It's an infinite line of charge. Then the electric field, if the line is positive, then the electric field will just point away from it. Let's say the distance from here to here is r. What did we say the electric field was? How does it relate to lambda and r for a line of charge?
1 over lambda, right? 1 over r squared.
1 over r squared. That would be for a point charge, it would be 1 over r squared. But for an infinite line, it should be slower than that.
Q
R. 1 over r. And then there were. Huh? What was it? Lambda? Pi epsilon naught r. This result we got for an infinite line of charge. Okay? So this result we need to remember because we would use it a lot. Yeah, it's something we will use quite a few times. And then we will today. We're going to derive the one for the infinite sheet of charge, which we will use probably even more times. For the dipole, it was r cubed. Yeah. It should be for an infinite sheet. It should be even slower than this. It should decay slower than this. We'll see what the result will be. So we did this. If you remember how we did it, we took a segment of length L, and we found the electric field in the middle. And then how did we make it infinite? We said let the length become infinite. Yeah, let L go to infinite. We did a ring last time, so here is a ring. This is the ring. And this is the radius of the ring. and the total charge on the ring was Q, and the question was, on the axis of the ring, an axis that goes through the center perpendicular to the area, so what is the, so if this distance from here to here is C, we found that the electric field will just point in the positive Z direction, right? In the Z direction. If it's a positive charge, of course it would be downward if it's negative. So we found that the electric field was, for a ring, was Q over 4 pi epsilon naught, and then Z over Z squared plus R squared. Remember that one? There's plastic. Now, we're going to use this result to now do the electric field for a charged disk. So that's our next goal for today, would be the charged disk. I'm going to use the other board to do that. So this one we went over. So now I'm going to, this would be the basis for our charge disk. So here is a disk. So now consider a disk. A disk of radius R and charge density. So disks are characterized as one-dimensional objects or two. Yeah, it's mostly this way, right? No thickness. Okay. So we're just going to worry about it. So it's two-dimensional. So the charge density will be what? Lambda or sigma or rho? Sigma. Charge density would be sigma for the disk. Okay? For the disk, it would be sigma. So here's our disk. Okay. This is the disk.
What this is this?
This is the radius R.
Oh, this.
That's a disk. And so a disk will have charge everywhere in the middle of it. Not like the ring. The ring only has charge around the perimeter. So for a disk, it's going to be just through. Okay. Am I missing something? Oh, okay. Okay. Yeah, anything? Anyone else? All right. And our goal is to find the electric field here along the Z-axis. By the way, I'm trying to make the disk to be three-dimensional. So the disk is here, like this. This is the disk. I'm trying to. That's what I'm attempting to draw. Disk is like this. The Z-axis would be this way, right? Above. Up. So here is the disk and the Z-axis. The question is, what's the electric field due to this disk at this point? It could, but we're not worried about it. Yeah. So let's pretend it's just a two-dimensional object. Thickness, let's say zero. If it has some thickness, then you would have a cylinder, right? So yeah, we'll worry about that. In fact, I do have a problem where there is a cylinder, a charged cylinder. I asked you to find the electric field for that. So let's do the, yeah. So the disk will have no thickness. No? So that's what we're going to do. So the idea is this. We know the electric field for a ring. And we're going to say our disk has many rings. It is made of many concentric rings. And let's see. Here's the ring. Let's take a ring here. And this ring will have a little thickness or a little width. Here's the ring. Okay, that's the ring. The radius of the ring is little r. The radius of the ring is little r, and the width this way is dr. Yep. The radius of the width of the ring is dr. Okay. So that ring will produce an electric field along the z-axis, right? Yes, if you have a ring, you get an electric field along the z-axis. Do we know the electric field for a ring? Yes, we do. Here it is. Okay. What would be the difference? The only difference is it's not going to be capital R here. It's going to be little r, right? And the charge on it is not going to be capital Q. It's going to be small dq, right? That would be the little charge on it. So we'll have this. The electric field contributed by that one ring is going to be called dE. And it's equal to, I'm going to just copy this. Right? We'll have dq 4 pi epsilon naught. And I have z here. The z of the director. And then here 1 over r squared plus z squared to the power. Notice z is a fixed quantity. Z is the distance from the center of the ring to here. That's z. Z is just fixed. The radius r of the ring is not fixed, right? You got small rings and you got the big rings. How big is the smallest ring? Zero. How big? I'm sorry. How small is the smallest ring? And then how big is the biggest ring?
R.
Radius r. Yes, all the way to the edge. So our integration limits when we integrate, they're going to be between 0 and r, and capital R. Okay. So now dq, we need to worry about dq. Surface charge density, dq is going to be sigma times dA. So that's what we're going to write here. We'll see the next step. We got z, 4 pi epsilon naught. Here I'm going to have sigma times dA. R squared plus z squared with 3 halves. Sigma, let's just write it. Here I need to write dA, and I need it's r squared plus z squared. 3 halves. Now dA. What's the area of this orange ring? It would be pi r squared if I included the middle. PR times the circumference.
That's the outer edge minus the inner edge, right?
So the area of the outer edge minus the area of the inner edge. Same idea. Yeah. So that's what we're going to do. And the idea is this. I always think of it as you take a pair of scissors, you cut from the middle and from this end, and you get yourself a little ring. Cut that ring open and open. And when you do that, you get this. It's dr this way. Dr this way. Approximately dr. When dr goes to 0, it will be dr. And then how long is it this way? This way? Yeah, it's going to be the whole, 2 pi r. 2 pi times r. And so the area of this would be length times width. It's going to be 2 pi r dr, right? dA, the area of just this little strip here, dA is going to be 2 pi r dr. It's negligible. R plus dr is basically R. Because dr is going to be 0. Yeah. So here, we're going to write our dA. So, can someone remind me? What should I write here?
2 pi r dr.
2 pi r dr. 2 pi r dr. We're going to lean a little bit here. The 2 pi is 2. So we have sigma over 2 epsilon naught. And then we have z not dz here, it should be what?
dr.
dr, yeah. The electric field would be this. The integral of this. So E sigma C to epsilon R dr R squared plus C squared to 3C. Those are the answers. So integrate that. It should be 1 over the square root. So it's going to be E is sigma C plus epsilon 1, and then you have 1 over R squared plus C squared 1/2 power, but keep the minus sign. Because when you take the derivative, you will get negative 1/2.
Yes.
Cancel that. And then the chain rule will give you the 2r dr, which will cancel the 1/2, which is not r dr. So that's the right antiderivative. And then you just evaluate between 0 and capital R. Let's see what you get. Just one z. 2 epsilon r. When we substitute capital R, you will get minus 1 over R squared plus C squared. In fact, yeah, you will get minus 1 over R squared plus C squared square root, right? To the 1/2 square root. And then when you substitute 0, you have minus becomes a plus, and then you have 1 over C squared square root, right?
Or z.
Yeah. So E would be sigma z 2 epsilon naught. And, yeah, what's 1 over the square root of z squared?
And 1 over z.
It's going to be, technically it's the absolute value of z, but z is above. We're just focused on positive z. So yeah, it's just 1 over z. And then minus this 1 over r squared plus z squared. And so, and then we just do one more modification. Take this z inside. So you get E would be sigma 2 epsilon naught 1 minus z whole r squared plus c squared. And where does this equation apply? For this charge along the axis of the disk, right? So now we're really, this one is an intermediate result. We want, here's the final result. One is to make the disk infinite. Is the one where I care about. So for an infinite disk means an infinite sheet. So for an infinite sheet, of charge density sigma. What's the electric field for an infinite sheet? Don't have to calculate. Yeah, you will do this. The electric field for the disk, but take the limit as r goes to infinity, right? The radius goes to infinity. Right? If the radius of the disk becomes infinite, then you have an infinite sheet. So what does that give you? I think you already said it, right? Sigma over 2 epsilon. Yeah, because if r, z is fixed, z is some fixed number. If r becomes infinite, regardless of what z, that fixed number is, this part here becomes 0. And 1 minus 0 is 1, so you just have the front. Sigma over 2 epsilon naught. That's the electric field for an infinite sheet. So this result, we care about it and we will keep it. We will use it quite a few times. First. Just to be sure, here's a sheet. Let's say it's a positive sheet. Plus. This is positive sigma. That's the sheet. And I'm just drawing the side of it, right? So imagine this sheet is like it's like this wall. This wall is positively charged here, and of course the wall is not infinite, but let's assume it's infinite. So this sheet is like it's coming out like this way, extends to infinity this way and back to infinity and then upward, right? It's infinity this direction. It's a two-dimensional sheet. And the question is, let's say I'm here. In what direction is the electric field due to this positive left? To the left, away. How much would it be? Or what would it be?
Sigma.
Sigma over what? 2 epsilon naught. Good. How about here? In what direction?
Right.
Right, okay. And what's the value or the equation? Sigma over 2 epsilon. How about here? Yes. Yeah. So if it's infinite, the electric field is just, you see, it's constant. Regardless of how far you are, the electric field is going to be constant. So still, sigma over 2 epsilon naught. Yeah, the area of the sheet is yeah.
Karena nggak di minus this one, nggak di minus.
Yes, correct. Correct. Yeah. 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 So yeah, so if you're really close to the sheet, you're affected basically by the charges that are here just locally. If you're farther and the sheet is infinite, you're now affected by an even greater amount of. So yes, you're farther, but you're affected by more charges. And so it averages out. You wouldn't know unless you mathematically do it. And the math tells you it's actually constant. It averages out to just be
Can you explain why the electric field for the sheet is equal to the electric field of the disk as the limit goes to infinity?
Yeah. So a sheet is infinite, right? So the disk used to be this small. What if I make the radius of the disk larger and larger?
Larger.
It becomes infinite, right? Yeah. That's why it's infinite. So that's that, right? Okay. We still have yellow chart. Let's use orange. So here is, we're going to make another sheet next to it, and it's going to be parallel to it. Here is the other sheet. And it's going to have minus. Minus charge, okay?
Yeah.
And let's make this one the same charge density but minus. So minus sigma. Okay? Now I'm going to ask you the same set of questions. What's the electric field due to this orange one?
Left.
In what direction? Left. And how much?
Minus.
Sigma over 2 epsilon naught. And left. Because it is negative, it's pointing left. Don't put double negative. You already put an arrow. Okay? How about here?
To the right.
To the right. It's towards itself. Okay. How about here?
To the right.
Towards itself. Okay. Yeah. Just happens. So I ask you, let's use red for this next one. What's the total electric field to both sheets combined here?
Zero.
Yeah, 0. One left, one right. 0. What's the electric field to both of them combined here?
Zero.
And then here?
Zero.
Oh, they flow in the same direction, yeah. So the electric field is actually, and that electric field is sigma over just epsilon naught. Right?
For both the combined.
So, just to put it in context of this class, imagine this wall is positive and infinite, and that wall is negative and infinite, right? Positive and infinite, negative and infinite. The electric field inside the classroom is this way, and outside the classroom will be
Zero.
Yes. So, when you have two infinite sheets, one is plus, one is minus, the electric field there will be electric field between them, but zero outside. Zero outside. Yes.
How, wait, so the sheet between the positive and negative on the left and right side, does the sheet block the way of the
No.
electric field? No. So it penetrates.
Yeah, the electric field just exists everywhere in space, yes.
So
Yeah.
what kind of sheet is that? It's like,
It does not matter what kind of sheet, yeah.
can we see the sheet?
Huh?
Like, can we see the sheet? Is it visible?
Yeah, it could be made of steel.
So is there anything
Yeah.
that, so I know that the field itself doesn't show any effects until you put a charged particle in it, but is there any material where, or is there any medium where that charged particle can't react to that field? Because the medium is too thick for the charged particle to shoot? Or would that just be?
What happens, as soon as the field exists, charged particles will react to it. However, if you put a charged particle here, it will experience how much force? Zero, because the combined field is zero.
But if you put it in the middle, since an electron does technically have like a volume, is there ever a material where, oh, I'm guessing, is there a requirement for this, that it has to be like some
Atau kayak
medium
pantulan
between the two,
pantulan
sheets that's the electron respond to it? Like, is there
Atau
ever a
kayak
material in between the two sheets where the
bukan
electron is
fisik.
not able to
Atau it's like
I think you're, for now, let's keep it vacuum. We will worry about what material we can put inside when we talk about capacitors.
Okay.
Can we see like that? I mean, can we see like
So, for now,
kayak
um,
dikasih like
we have this one, this sheet, and this sheet. So this could, okay, well, we'll talk about dielectrics when what you put in between here in about 2 chapters. But, oh, that's my yellow
kalau
check.
kamu masukin di
All right. So this configuration is called the parallel plate capacitor.
Ini
That's right.
harusnya kita bisa lihat bahwa
This meaning referring to this, you got an infinite sheet and another infinite sheet. So this is called
kita bisa pakai
a parallel.
juga ini serbuk besi dilempar pakai magnet. It's always magnetic field. You can see it.
Okay. We talk about capacitors as a component for an as a standalone thing, and then how to make this thing, this quantity called capacitance larger or smaller when we talk about capacitors. But let's just mention this configuration is called parallel plate capacitor. They come in different shapes and forms, but the basic is this: you got a plate and another plate. There is an area between them. The electric field between them is something if they're charged, and outside it's essentially zero. Now, you know capacitors are used in electric circuits, right? And none of them is infinite. They all fit within the whatever equipment you have. So what's going on? We said here it's infinite, and then over there it's something that fits conveniently in your radio, cell phone, whatever, or driver. And the answer is, when we say infinite, that's an idealization. It's mathematically, yes, you need it to be infinite to have this exact thing. But if it's large enough, then it would be considered infinite enough, and then we use this as the approximation. So for example, here is an example of a parallel plate capacitor. Here is a sheet. In fact, we'll do an example with this. So let's say it's 10 centimeters this way, or 100 millimeters this way. And it's 100 millimeters this way. Right? 10 centimeters is 100 millimeters. And let's say here's the other sheet, or other sheet. And let's say the distance between them is half a millimeter. Notice the area, the dimension of the area is so much bigger than the space between them. It's what, 200, 0.5, let's say. It's like 200 times bigger, right? So that's infinite enough to use the approximation that there is field between them if they are both charged. If this one is, let's say, positive, it has plus charges. And this one has negative charges. Then you will have a field from the plus to the minus, but not outside. So again, it's not infinite, but it's close enough. So if these dimensions are so much bigger than this, we're going to just say the electric field is, or the electric field between them is going to be sigma over epsilon. Alright, so we're going to do an example, or a couple of examples of this. Can I erase both of these sides?
So the person who goes is from biar konsiderasi tujuannya kan ya misalnya di sini misalnya bikin sheet segini kalau bikin sheet segini kan gede prefer fokus segini kan nggak mungkin lah di dunia ini ada sheetnya gini.
Okay. So with that, let's imagine we have those two plates there. One of them is 10 centimeters each direction, and then they're half a millimeter between each other. Okay? Let's just have those. So here is the first one, and here is the second. Okay? And I will have them a certain distance apart. I'm not going to draw this dimension. Okay? So we would start with them both neutral, not charged and not charged. Not charged doesn't mean there is zero charge. It doesn't mean it's just empty space. It just means there are equal amounts of pluses and minuses. So let's imagine we take an electron from this one and place that electron here. Right? Take one electron from here and place it here. What's the net